So the second thing that we're going to learn how to do with solutions is think about their concentrations and think about solution formation quantitatively. And there's two kind of components to this. The first might be just to determine what the concentration of a solution is by mixing together a certain amount of solute and solvent. And then the second piece might be to take an existing concentration of a solution and interconvert it into concentration in different units. So we're going to go through exactly what that means. But just reminding us, we make solutions by mixing solute and solvent, and in general, the solute is present in smaller amounts than the solvent. And we can have different phases of solutes and solvents. We can be mixing two liquids together. We can be mixing a solid solute with a liquid solvent. We can even have gaseous solutes that are dissolved in liquid solvents. Okay, so first little piece when we think about sort of quantifying solute or solution concentrations is thinking about counting the number of particles we have. And this will have a significant part to play when we talk about colligative properties. So ionic compounds not only dissolve but dissociate, break apart into ions, and are going to make more particles than if we have a covalent compound. Covalent compounds like table sugar will dissolve but not dissociate when they make a solution, but ionic compounds like table salt, sodium chloride, will dissolve but also dissociate and will break into two particles, a sodium cation and a chloride anion. So counting the number of particles is sort of the first level of sort of quantifying here, and that's going to play a significant role when we do colligative properties in our last little section here. But importantly, we do want to think about how we not only determine concentration, but interconvert concentration. So at its core, remember that concentration is really a ratio between the amount of the solute. So this is always going to be the solute in our numerator. And you'll notice here I'm using the word amount because there's different ways that we can represent amounts. And we'll get to that on our next slide here. And then over the whole. And that whole might be the components of the solution, solute and solvent, or in some cases it might just be the amount of solvent. So we'll see these played out sort of on the next slide as we sort of break out the different ways we know to think about concentration. One of them that you already know is molarity, right? Remember, concentrations are always a ratio. You have a numerator and a denominator. The numerator is always going to be some amount of solute. And so the first sort of set I'm going to go through here always are talking about moles as your amount. So molarity is moles of solute per liter of solution. So we're really talking about solutions being a mixture of solute and solvent. Molarity is pretty straightforward. We've talked about that before. Now, molarity is not something we're going to likely see when we do colligative property calculations, but since molarity is very familiar to chemistry, you might be taking a solution that's in molarity and needing to convert it into other forms of concentration. A common one that we're going to see with colligative properties is something called molality. It's little m. That can be confusing because sometimes in our equations we see little m representing mass, but little m is molality. Same numerator, moles of solute, different denominator, kilograms of solvent. Okay, so we'll talk about on our very last slide here how we think about interconverting different concentrations of things, but those are two that have to do with amounts represented as moles. Another one that has to do with amounts represented as moles is something that we call mole fraction. You'll see this represented by a capital X, and you'll generally see as the subscript, am I talking about mole fraction solute or mole fraction solvent? Remember, a fraction is just part over whole. So again, the part, the numerator, is really just either moles of solute or moles of solvent, depending on what mole fraction you're interested in. So it's the part, in this case, moles of solute, over the whole, which is the combined moles of both your solute and solvent. So that's mole fraction. Hopefully not a stretch to recognize that if you wanted to figure out the mole fraction of solvent, all that changes is your numerator. Now see if this makes sense. If we have a two-component solution and we have one fraction already determined, the other fraction should be 1 minus the first fraction, right? So that's an easy way if you needed, for example, both of these for some reason. You could figure out both of them, but their relationship is that they both will add to 1, okay? So 1 minus one of the mole fractions will equal the other one. Okay, so these are all of the different concentrations where the amount is represented by moles of solute or moles of solvent in the numerator, and then different representations of the whole of our solution in the denominator. Two other ones to sort of mention, and we're not going to see these in colligative properties, but they are important because you will see problems that ask you to interconvert concentrations that may take on this form. And that's either volume percent or mass percent. So again, these are going to be fractions or ratios of a part, volume of solute or mass of solute, over the whole, the volume of the solution or the mass of solution. Now again, because we are representing these as percents and not fractions, we see a multiplication by a percent here, so we multiply by 100. And an important thing to sort of remember when we're doing some of these calculations and manipulations with solutions is we cannot add volumes together. And I know that seems a little counterintuitive, but that's just how the science works for it. If you mix two volumes of solutions together, A plus B, or let's say 100 plus 100, might not equal 200. And I know that math doesn't make sense, but it's just how the science works when we're mixing solutions together, that interparticle mixing might not be additive. However, masses are additive. If you had a 100 gram component and a 100 gram component, mix them together, you're going to get 200 grams. So that's an important piece to remember. Okay, so here's a little strategy when we're thinking about how to do these quantitative pieces with solutions. Again, the first thing that you might be given is you're given amounts of solute and solvent, and you have to tell me the concentration of the solution. In general, you're going to be given things that come from laboratory experimental data, maybe a mass of a solute or a solvent, or a volume of a solute or a solvent. And then you just need to know, depending on what kind of concentration you're determining, how to use that initial data and get the numerator and denominator pieces that you need to figure out the concentration. Okay, again, remembering that concentration is always going to be some amount that's in your numerator as your part. That's always going to be something related to solute. And then your denominator is going to be something related to the solution, and it might just be pure solvent. For example, if it's molality, it's going to be kilograms of solvent, or it might something to do with the solution. So key to these is recognizing a lot of those had like moles of solute or moles of solvent somehow. If you are given a mass, molecular weight is what you will use to interconvert mass and moles. Okay? If you need to convert mass and volume, I must use the density of the solution. So you must be given the density of either the solution or the solvent or something that allows you to interconvert these terms. Okay, so density can be an important piece. Just a little reminder, if we've got masses that we're combining together, for example, what is the mass of the solution? If you know the mass of the solute and the mass of the solvent, you get the mass of the solution. In another way, if you know the mass of the solution and you know the mass of the solute, the difference of those two will give you the mass of the solvent. That might be important if you're figuring out molality. Okay, volumes are not okay to add or subtract to one another. So again, putting all of these pieces together can allow you to do these quantitative pieces for solution formation and use them in one of two types of problems. Either determining the concentration of a solution and maybe using it in a colligative properties problem, or maybe I'm asking you a question to interconvert sort of how we're representing those concentrations. Both are kind of fair problems that you'll see in this quantitative aspect of solution formation. Now, the last piece is to highlight that if you're given one of those volume percents or mass percents, those are unitless, right? If it says mass percent, there's no units with it. Volume percent, no units. So here's what you do. You give it units that make sense. You give it units of mass in grams, and you can give it units in volume in either milliliters or liters. Now, here's the key. Whatever number you have for the percent, let's say it's a 5% solution, that number becomes the number of the unit of your solute. So for example, if it's a mass percent, it would be 5 grams of whatever your solute is. Here is the key. You always have 100 units of your solution. So it's either 100 milliliters of your solution, 100 grams of your solution, whatever the unit is you have for your numerator, you're going to have the same unit for your denominator. And that's an important piece, because if your starting point is something with a percent solution and you need to convert it into molality or molarity or something like that, you need to give it units in order to do so. And that's how you'll do that. And that's it on determining quantitative aspects of solution formation.